in the previous video we actually talked about the summarized form of all our loadings, alright, the longitudinal, transverse and shear loading, and we somewhat also say that there is a rule of mixture model, if you still remember, alright. And then we say that for all the loadings, alright, we assume that the Poisson ratio of the material is the same, alright, and we say that we're gonna discuss with this in this video. Alright, so the Poisson ratio by definitions is the ratio between the compression and the tensile. Okay, so when you have a material, if you were to pull this thing, alright, this is the tensile. So when you pull this thing, okay, there is a certain form of a compression in this manner, okay, in this thing. So if you, for the sake of better illustrating this thing, let's watch a video. Okay, let's go.
Take an example of a rubber strip as shown. When we pull this strip in a longitudinal direction, the strip elongates in a longitudinal direction and contracts in a lateral direction. The strain developed in a longitudinal direction is known as longitudinal strain, and the strain developed in a lateral direction is known as lateral strain. Now, when we take the negative ratio between this lateral strain and the longitudinal strain, we get Poisson's ratio. Poisson's ratio can be represented as Poisson's ratio describes the relative change in the lateral dimensions of an object when the load is applied in longitudinal direction and vice versa. Poisson's ratio for some of...
Okay, I think you have understand. So just to add on to the meaning, okay, allow me to give me one, is that the Poisson ratio is a negative value, first of all. Why? Is because we're talking about the lateral strain, alright, trying to be compressed. When we're trying to be compressed, we are actually looking into trying to move in a negative direction. When you pull something, you're actually going in the positive direction. So if you were to compress, you're saying that it is minus, alright. And with this understanding, you have a lateral strain which is a minus, alright, divided by the longitudinal strain which is going in the positive direction. Alright, so the minus divided by plus, you still get minus. Alright, and this explains why this is minus. Alright, and the symbol for this is nu, but as for our symbols for Poisson ratio in our context is V. Alright, it's a curly V. Alright, so let's start now. Ouch. For as come back to here, this is our V12, our Poisson ratio. So don't confuse yourself with the small v with your capital V, the volume fraction. Alright, and don't confuse yourself with V as telling yourself as this is the volume. Alright, because in the previous context we keep talking about V and V, alright, which is all this V. And think about it, this V is not your meter cube, not your volume. This V is a certain ratio, okay, that is multiplied with your Young modulus to get the overall Young modulus. So in all, this is, for example, this is transverse one. All in all, we are calculating or doing is to get a ratio of the Young modulus only, alright, between the matrix and the fiber. Alright, and we are not talking about the volume itself in the meter cube. We are only dealing things with the ratio. Alright, so the V, capital V, is talking about the ratio of the volume. Alright, and I may be wrong, alright, but from the trend I'm seeing now or looking now, this is most likely the case, and I may be wrong. Anyway, let's continue. So therefore, this small capital V most probably and correctly, I may be wrong again, is that this is the Poisson ratio. Alright, it's a Poisson ratio, and is the minus epsilon 2 divided by epsilon 1. Which means that this thing is your lateral one. This is the longitudinal one, right? As we have said just now in the picture all along. The lateral divided by longitudinal. Okay? So therefore it is the ratio of the strain in the two direction. Alright, this is the two direction. If we were to go into 3D, alright, this is our matrix, this is our resin. We are pulling in the one direction. This is the two direction. And therefore, alright, if you are looking at the top view right now, alright, your two direction is actually in this direction. Okay? By right, this should be the third direction, the E3. But I think in a certain sense they are trying to simplify things in terms of a 2D system, not a 3D. Alright, so therefore they are actually talking about the strain in the one direction. This is the one direction, or when you pull this thing, or when you pull this thing will actually contract. Alright, and this contraction, alright, is the change minus change of the strain, alright, which is in the towards the two direction. Okay, so therefore this is the visual explanation of this formula. Hopefully this will make you easier to memorize. As the name suggests, 2 in plane, so it's just a 2 in plane Poisson ratio. Alright, so it's a 2D in plane, I will believe. Alright, so therefore it is convenient to label things in terms of Poisson ratio 1 2 and Poisson ratio to 1. Poisson ratio to 1. And 1 2 is the major, while the 2 1 is the minor. Okay, and whenever you see 1 2, it tells you about the longitudinal, alright, because it starts with the 1. Alright, if it's talking about 2, then this means that it's talking about the 2 direction, which is the transverse. Alright, where over here I don't think it's talking about any transverse, but it's just simply saying that it's a minor Poisson ratio. Why is that? It's because it changes in the 2 direction first. For example, if you're pulling in this direction, you're exerting in the one direction loading, alright, because you're applying loading in the one direction, and the changes in the 2 direction is determined by how large the load in the one direction is. Alright, so the 2 direction is somewhat like a subset. Alright, is whatever changes in the one direction will give changes in the 2 direction, which by a certain extent is not very significant, although there is a certain strain in the 2 direction being compressed. Okay, so if you're talking about a loading in the one direction, it means that there is no loading in the 2 direction, right? This is the 2 direction. If I were to label them, okay, this is the one, and this, the red color, is the 2 direction. So in the 2 direction, there is no loading in here. Alright, so there is only compressive due to the one direction, and this is why this is called minor, because it is a minority system compared to the major one. The major one is the one that is being pulled, right? Pulled to, I think you get what I mean already lah. Okay, so it is easier for you to memorize. So wherever it's 1 2 is longitudinal, 2 1 then is minor. Future, if there is more complex way of explanations or more things that to be updated, I'll just update with a next video or things like that. But anyway, let's just continue. So this means that the two of these Poisson ratios aren't the same. Alright, because your Poisson ratios, you are taking about the ratios between this direction and the changes in this direction. Alright, while the 2 1 direction, the transverse one, is talking about this direction. You are pulling in this direction. So this thing over here, oh, now after I explain, then I realize, okay, more a better one explanation now. Okay, let's start the explanation. Okay, so when you apply a longitudinal system, alright, the strain itself over here is pretty much significant. There is a big strain. However, if you were to take a look, if you were to apply, alright, if you were to apply, maybe I should draw this thing. If I were to apply a force in this transverse direction, alright, there will be a compressive in this direction. Alright, previously was that you apply in this tensile direction, the compressive is going here. Now if I were to terbalik, go in the opposite one, this one is being pulled while this thing over here is being compressed, then you think about it, this is much lesser. The one that is being compressed is really very little. Okay, and this is the reason why they are calling it the minor Poisson ratio, and for over here the strain is much larger as compared to the strain over here. Think about it. Alright, I no need to do experiment, but from your past experience in life, most probably yes. So therefore, yeah, this is the major Poisson ratio, and this is the minor Poisson ratio in terms of the explanation visually. Alright, and therefore it is pretty obvious that they aren't the same, and that V12 must be much larger than V21. Okay, so after knowing all this, then what can we do about it? In the exam, the most important formula you're going to use is this one. Okay, because as you see, alright, these things are in terms of the fibers Poisson ratio and the matrix Poisson ratio. Alright, so in the end, they're only actually asking you to find the Poisson ratio of the whole composite, because the whole composite is being pulled in this direction. Alright, this means that the Poisson, the matrix, alright, and the fibers are put together as one. So when you pull, what is the total Poisson ratio of the material? So you are trying so what we have done so far is trying to create a property for your material. So you are trying to determine the overall properties of your composite, alright, when the matrix and the fiber acts together. Alright, so you are trying to create a property sheet or property menu or properties, I don't know what property table, alright, to give you a specifications of your composite itself. So this is the equation that you're gonna use and memorize, alright, where this one I have explained. So this one I think very much familiar to you. This is just the ratio between the fiber and the fiber itself. Right, and yeah, this one, if the fiber is 0.6, alright, then this one most probably is 0.4, right? So therefore this is 1. I think you get what I mean? Yeah. So therefore you just memorize this one will do. Okay? And next up, alright, is the things that I'm gonna derive this one. So if you want to continue to watch, you can continue to watch. Otherwise, you can just skip to the next video if you are looking only for the formula, and that's it. Alright, if you are keen to actually watch how the derivation comes about, I'll continue within this video also. Alright, so I cannot confidently say that I can successfully derive this, but I will try. So if you want to go, you can go. Otherwise, let's continue. Alright, so let's start for the derivations. Is that the first derivation is that they're talking about a initial notation. Alright, initial notation. If you don't know anything about initial notation, or if you forgot, you can come to this my channel, okay, and you go to created playlist, alright, and you can see SEM3 mechanics 4n, alright, and then you can just search for initial notation. You go Control F and then initial notation. Most probably you can see a few stuff coming out. I think, yeah. Alright, so yeah, then you can just see lah. Okay, so I'll not go through the things within the initial notation stuff. I'll assume that you have understood, but it's pretty simple. Alright, just saying that V, okay, in other words, the Poisson ratio or Ij, alright, in two directions, because if you think about it, when you pull this is in the I direction, and then when you pull this, the compressed system is in the J direction. It's like a 1 and 2, that's all, but they are just writing in a more general term, I and J, okay, and therefore this is the exact formula that we have just seen in the earlier part just now. So therefore for a transversely isotropic material, so for a material that is being transversely pulled, alright, so instead of pulling in this direction, you are pulling in this transverse direction, alright, and it's an isotropic, meaning the material is how do I say, has equal resistance, in terms of strength, alright, it can tahan strength in all directions, all the same, alright, wherever you pull, the forces required are all the same, alright, so this means isotropic, alright, and therefore it means that over here the Poisson ratio of 1:2 divided by Poisson ratio of 2:1, alright, the one that we have just said earlier, the major Poisson ratio divided by the minor Poisson ratio will give you your Young modulus in the one direction divided by Young modulus of the two direction. So these things imply that the ratio between the Poisson ratios, alright, is the same as the ratio between the Young modulus in the two directions. Alright, so somewhat in a certain sense, the Poisson ratios are the same compared to the Young modulus ratio also. Alright, so this is something I think most probably is after certain experiments, then they will set this as equals to each other. Okay, and I decided to actually go into deeper, alright, to actually try to solve for why is it like that, mathematically, and I realized that in and out there may be a certain understanding that I've not understood. V12, for example, is minus epsilon 2 divided by epsilon 1, the strain, right? So Strain, you know from the Hooke's law, is sigma equals to Young modulus times strain. Okay, I'll be going a bit faster, so some terms I will not repeat myself again. Alright, so the E will actually go down, so stress divided by the Young modulus will give you the strain. So I sub in the strain as stress divided by E. I will have all this thing. So epsilon, I will change it all to here. Okay, this is for V12, and for the Poisson ratio V21, I did the same thing. And for the Poisson ratio, alright, the relationship is V12 divided by V21, and therefore I took this V12 divided by V21, and I might have this thing over here. Okay, this is V12, the same thing, you can double check, and my V21 is over here, right? Oh, my V21 is like that. Okay, so you give me a while. Yeah, so after I did this, okay, so this is the last step that we have done, and I switch. Okay, when I switch them, you give me a while. So I would switch sides. So I'll take this thing, okay, I'll bring it over here. So this portion over here, I'll put it over here. Maybe I should write it down, okay? And the divide, you know, if you were to change to times, this thing over here will flip to the bottom, this one will go up, right? This is just the math, if you remember, very simple math, okay? So I'll have this thing. As you can see, your sigma 2, alright, this thing times this thing square, so I will have this thing divided by this thing times this thing square. So this one should be divided. Okay, yeah, so I think you get what I mean. So I'm rearranging stuff only so that it is easier for you to see. So I have this thing, or you may wonder what the hell did I divide and then change to times. Alright, over here, this actually I skip step lah. So this step should be, after that is this step, then this step really becomes this step. Okay, so hopefully this is clear. So if I change divide to times, alright, this means that I'm flipping. Hopefully this is pretty clear for you, I guess. So for example, 5 divided by 3 times 2 divided by 4, maybe divided by 2 divided by 4. Okay, so I would say that 5 divided by 3 times 4 over 2. Alright, you can work it out in your, so you can take this, alright, and this you put inside calculator, you should get the same answer. I'll not go through with you, but at least you get the meaning of it. Alright, so once I get this already, next is that same thing, I do again the switching sign. So the divide I change to times again. Okay, so I bring in all the square in all the numerator and denominator. So sigma 2, I'll have this thing, you see, sigma 1 square, because I changed the divide to times already. Alright, so sigma 1 square and E1 square. Then next, the divide I change to time, so E1 square and sigma 1 square over here. Hopefully this is clear. That's why I say I'm rushing as a train now, because it takes a lot of time. Anyway, so this is this. Next, so if I let sigma 1 and sigma 2 as equals to each other, alright, then I can cancel out them. Then what I will have is E1 squared divided by E2 squared. Alright, and for some reason, alright, the square somewhat is being removed, and this is why I have E1 over E2. Alright, and this is the Poisson ratio system. And as you can see, we have derived from the V1 to V21 all the way to something E1 divided by E2 square. So the square, I don't know go where, end up becomes like that. But at least you see the system that is coming in. Alright, nonetheless, you can also visit the website that is given in the presentation slide. Okay, so which is over here lah. Okay, this blue color link. Alright, hopefully you can see. I don't know lah, but anyway, yeah lor. So over here they say that for transversely isotropic material, this relationship exists. Alright, so how does this exist? Is it an experimental existence, or is it a mathematical derivation? So I decided to derive, but I don't know where the square go. That's the last step that I can't solve. But at least you see the result. But I haven't finished yet. Alright, I'm only doing the second step only. Okay, next, over here they also kind of a skip step. What do I mean is that if you remember, your Poisson ratio 1 to, for example, alright, is equals to minus epsilon 2 divided by epsilon 1, which is, yeah, you think about it lah. Okay, I will not go through. Alright, V12 is this one. Okay, so if I were to rearrange in terms of epsilon as shown over here, I would have V12 times E1 is equals to minus E2. Okay, if I were to bring this to plus and this one minus, I will have my epsilon 2 for the fiber. Alright, so the strain in the two direction for the fiber, that's the meaning of that. So there is a strain in the two direction, so this is the thing. Alright, you are going in the two direction for the fiber only. Alright, so for the shaded part, the fibers. Okay, hopefully this is pretty clear. So for the strain in the two direction for the fiber, alright, this is the answer for the fiber. Alright, and then after which they rearrange the strain. Alright, you use the Hooke's law, alright, which is the stress equals to E times the epsilon. You eventually get this thing. Alright, so this thing over here you sub in as using the Hooke's law. Alright, you'll get this one for the fibers. Okay, hopefully this is pretty clear. Alright, same for the matrix. Alright, the matrix is the same thing, using the same way that I've solved for it. Alright, so once they have this form in terms of a Young modulus, okay, then what they actually do is that they add up the total transverse strain. Alright, so they add up the epsilon 2, because we are actually looking at the epsilon 2, and I don't know why they are looking at epsilon 2, but let's see how it goes. Okay, so what they took is they took this one. Okay, where's my this one over here, they actually bring it over here. Alright, except the minus sign lah. Okay, and then over here, alright, this one, they actually bring it to here. You see, sorry, only here. Okay, and you may wonder what is the F and what is this. This is actually the volume fraction. Alright, this is the fraction of the fiber, this is the fraction of the matrix. If you remember, 1 is equals to the fiber plus the matrix. So the matrix, if you want to find the matrix, you can just say that 1 minus F is equals to matrix. So this is why it's over here 1 minus F. Okay, so once you get this, alright, you eventually get a strain in the two direction. Alright, and under axial loading, the equal-axial strain condition is this thing. Because remember just now the minus sign is over here, there is a minus sign over here, so they bring the minus sign out over here. Okay, so the minus sign is over here lah. Okay, so they factorize out the minus sign and includes the ratio. Okay, so it makes things more neater. Alright, it's still in the form of the rules of mixture. If you think about it, it's because it's the mixture rule, the percentage of mixture that you mix inside. And over here, they actually rewrite using Hooke's law, strain. Okay, I don't know why they at first they expand from the strain to this one, then after that they contract again. But anyway, so the strain, alright, they using the Hooke's law, alright, this thing over here, the stress divided by Young modulus, you divide, you get back the strain. Okay, so you do this, you get back the strain. So this is the same equation. Okay, they rewrite it. So therefore your strain in the two direction, alright, is then rearranged again. Alright, so they rearrange in this form. And the next step is that they factorize up the epsilon 1. Okay, they factorize out the epsilon 1, and what we have is minus epsilon 1 F plus this thing. Okay, so then after that they bring this, alright, to the denominator. So you have epsilon 2 minus epsilon 2 divided by epsilon 1, which is this one. You see, so if you were to, so they'll set it equals to each other. Okay, so this thing over here is this thing, while this thing that I've done is this thing. Okay, so they're actually factorizing out all the stuff. Alright, and then as you can see, this thing is actually your V12. Okay, so if let's say if you want to have a V21 in this case, if you want to calculate V21, then they're bringing another formula, they're bringing this one. Okay, so they know that the V12 divided by V21 is equals to your V12 is equals to this one or equals to this one, so they put it in over here, or V21 is equals to, so sorry this thing over here will be equals to E1 divided by E2. Okay, so I know, so with this understanding that we have derived already, and also this understanding, what they do is actually to rearrange in order to find V21. So what I do is you bring this upwards. Alright, so what I have is V12 multiply by E2, because you bring this thing upwards, right? divided by E1. Okay, and then alright is equals to, so wait, yeah, so this is V2 1. So you know that your V12 is this one. Alright, so therefore it's also equals to this one, right? This thing is equals to this, which is also equals to this. So therefore you sub this thing as your V12, which is why this whole thing over here is your V12, or E2 E1, and it equals to your epsilon, your Poisson ratio V21. Okay, and this is how you derive all these things. Allow me to repeat as a summary, so at least it's more clear, because I think that I ran too fast, so that it's very blur. So the Poisson ratio, you know, is the lateral strain divided by the longitudinal strain, alright, where your V12, alright, is equals to strain 2 divided by strain 1 minus, alright. And then after that, alright, the next thing is totally different from this already, is that you take your Poisson ratio 1 2 divided by Poisson ratio 2 1, which they say that the relationship exists, alright, mathematically and or experimentally. I think they are equals to each other. Okay, this is something that is a bit blur, but at least you understand how it's being derived, which the long one that I've derived just now. So over here next, over here, you can say that this is equation 1. Okay, next is that they want to derive an equation for Poisson ratio of 1 2. Why do we do that? Alright, so the reason of us doing that is because under axial tension, alright, when you're pulling this, or maybe this is the object, when you're pulling this object, alright, there will be a strain in this direction, in the negative direction going in here. So we are actually kind of keen to look at how does this thing affect your composite. Alright, if you were to pull in this direction, will this thing over here contracts? And if this contracts, you're gonna cause some cracks all over here. Okay, and therefore this is also the reason why I think they're actually looking for epsilon 2 in the 2 direction. So whether will the transverse system, or will it actually cause your fiber to crack? Because if you were to go in this direction, your fiber is arranged, maybe I should use a different color. Your fibers is arranged in this direction. So if this thing gonna push here, you're gonna crack your fiber. You see, you're gonna crack your fiber. So we're actually keen to look at how will the matrix and the fiber be cracked. So therefore they utilize this equation where epsilon in the 2 direction, or the strain in the 2 direction of the fiber, or it can be rewritten as this thing based on this formula. Okay, alright, so this formula is also this formula, it's just in terms of initial notation. Alright, so they rearrange already, they get this. For the matrix they also get this. Alright, and then after that they will add up all the strains, which is why you can see there's a plus, and then with the certain ratios of the fiber and the matrix. Alright, and then you rearrange, you will eventually get this one, the Poisson ratio. Alright, and we can say that this is 2. Next, you apply 2 into the 1, alright, and solve for your V21. And this is why we have the Poisson ratio for our 2-1 direction. Alright, and therefore this is the thing that we're talking about. Alright, and I hope that this is pretty clear, and I'll see you in the next video.